This is Lab 5 by Ansh Modi. Introduction. Our aim in this lab is to observe and model the Lenz's law, which occurs when an induced current creates a magnetic field, which then exerts a force on the source of the external magnetic field, and the induced current is made by an external magnetic force. In this lab, we observe this interaction by dropping a magnet through an aluminum tube. We then modeled this in GlowScript and compared our experimental results with our model results. Principles that we used in the experiment. We used Faraday's law to calculate the EMF, which was the change in magnetic flux over time. We used the Biot-Savart law to calculate the magnetic field, and which is used to calculate the magnetic flux using this equation here, which is the integration of the cross product of the magnetic field and the area. And then we used Newton's second law to model the force on the magnet due to the induced current's magnetic field. Methodology. We first measured the dimensions of our aluminum foil, the length, the width, and the radius. And then we found the north pole of the magnet using the magnetometer app. Then we dropped the magnet through the aluminum tube and recorded a video of it. Then we used timestamps to find when the magnet went into the tube and out of it. And then we repeated this 5 times and calculated an average time. Observations. The magnet took longer to fall through the tube than going through free space. This is because as the magnet falls into the tube, flux increases, which induces a current in the foil. This current creates a magnetic field that pushes on the magnet upwards. And as the magnet is leaving, the magnetic flux is decreasing, which also produces a current which pushes the magnet upwards because the direction of the magnetic field changes once the magnetic field is moving downwards. Measurements. For length, we got 0.3048 meters. For width, we got 0.005 meters. For inner radius, we got 0.015 meters. For our times, these are our times. We scrubbed through the video to find when our magnet entered and exited the video using the same reference point. So I think we used the bottom of the magnet. So when the bottom of the magnet went in and when the bottom of the magnet came out of the magnet. The average we got was 0.63 seconds. So this is our GlowScript, and then first we started off by establishing values and the constants that we used throughout the experiment. So, over 4 pi, and the resistivity of the aluminum, and then the gravitational constant, and then we initialized the graph. And then we inserted the measurements, so the length was 0.3048 meters, etc., etc. Then we created 2 functions, one to calculate the magnetic field of the bar magnet, magnetic field. So it was called dipole B, and it used the Biot-Savart law equation. And the second function calculated the magnetic flux using the previously mentioned equation. And then we used a while loop, to measure the position of the bar, and from the start when it goes in and when it comes out. And then these are all the functions, and this is like to test. The next step is the bar magnet inside or outside the loop, and this is to calculate the gravitational force of the magnet. This is to calculate the magnetic force from the tube, and we use the flux stuff. And then using all of this, we find the net force, the net magnetic force. And so we can use this, we can find the change in velocity and then thus the change in position. And this all creates a graph. So these are the results of our simulation. It took 1.306 seconds to go through the tube. Additional questions. What if the resistivity of the conductor were reduced as close as possible to zero? How would this affect the dynamics of the falling magnet? If the resistivity of the conductor were reduced, then the induced current and magnetic force would increase, which would result in the magnet falling slower. What if there were holes or slots cut into the tube? How will this affect the rate currents in your model? If there were holes or slots in the tube, the resistance of the tube would increase, which would then decrease the current, causing the magnet to fall faster to the tube. That's it. Thank you.